Hello. So my problem is on simulate unsteady flow in a pipe with a pulsating velocity inlet using the user-defined function. To solve this problem, we will use fluid flow fluent, and there we will create a geometry in new design modular. We'll set the units to centimeter and take the XY plane where we will sketch two circles. And give dimension to the outer radius as 20 and the inner diameter of the pipe 18. So the thickness of the pipe will be 2 centimeter. And generate and extrude. We'll give the length of the pipe 80 centimeter. Generate. So our pipe model is completed. Now we will use tool and fill this hollow space with fluid. Apply and generate. So as you can see, two bodies, two parts, one is solid, and we will name this is fluid, but its name is solid, so we will write it as fluid and generate. Okay. So our modeling is complete. Now we will start meshing. In meshing, we will insert method, select the whole body, apply, and use tetrahedrons and click generate. As we can see, the geometry has all the meshes in it. Now we will name the faces. Use face, click on the face and create name. This will name as inlet. Okay. This one wall. Create wall. And this page is outlet. So our meshing is complete, and we have given the name inlet, this side, wall, and the outlet. So our meshing is complete. Now we will move to setup. We will update the mesh and move to setup. Here we will use double precision and solve processor 4. Start. This is our geometry. In our expression, the velocity is a function of time. So the velocity will change with time. So we will put this as transient. And the material, will select new material, fluid database, select water liquid, copy, close, create and change and close. Now we will set the fluid to water. In cell zone condition, you can see the material name is air. We will change it to water liquid, apply. So now this portion here, this is water liquid and this is solid aluminum. Now we will give the boundary condition at the inlet. As in the question there is an expression. We'll write the expression in here. expression. Now we'll take the mean velocity as 1 multiply bracket 1 plus, and we will take the amplitude as 0.5 multiply sine bracket 2 multiply pi, we will constant pi multiply 2 hertz. We will give 2 hertz each z bracket close, then again multiply with time and bracket close. So this is the expression we are given at the inlet, where 1 meter per second is the mean velocity, 0.5 is the amplitude, and 2 hertz is the frequency of the pulsating velocity inlet, and the time. We'll click apply, OK, and apply. So this expression will only be applied in the inlet, and as the fluid moves on, the velocity of the fluid will goes on decreasing. Now we will go to run calculation. We'll give the time step to 100 and number of time step 100 and time step size 0.01. It will give us the 1 second velocity time graph. We'll start calculating. One small mistake, I didn't choose the velocity time graph, so I'll stop this calculation. Go to report definition, new surface report, area weight average, and at the we will select the inlet and velocity magnitude. Okay, now this will give us the graph of the velocity and the time. So we'll start calculate. Okay. So let me define the explain the graph. As you can see from the graph, the mean velocity of the fluid is 1 meter per second, and as we have give the amplitude 0.5, the velocity of the fluid will fluctuate from 1.5 to 0.5. As you can see, it dwells down to 0.5 and again increases to 1.5 at the inlet for 1 second. So now if we in the question, I have to monitor the axial velocity at midpoint and outlet. So we will create new plane, select XY plane, and our midpoint of the pipe will be 0.4, and name this plane as midpoint. Let's name it as mid plane. Okay, create. We have created the plane. Now we will again go to report definition, new surface report, area weight average, and select the midpoint and velocity magnitude. Okay, now this will give us the velocity of the fluid at the midplane, which is the 0.4 meter of the pipe. We will start calculate. Okay. So this is the one. So let me explain the graph. As we can see, the velocity of the fluid has gradually decreased to 0.4 meter per second, and it increases to almost 1.2, say 1.2. So and its mean velocity may be in between 8.5. So as we can see, in the midpoint, the fluid velocity gradually decreases to 0.4 to 1.2. This is the velocity time graph of the fluid velocity at the midplane. Now at the outlet section in the question, I have to also show the outlet section. So we'll do the same plane xy. So 0.8, and this will be the outlet. Create object same name already exists, so we will give this at outlet 1. Create, close. Now again we will do the same, new surface report, area weight, pressure, velocity magnitude, and we will take the outlet 1. So this should give the velocity of the fluid when the fluid reaches the outlet. So we'll calculate. Okay. So it is the same graph as the before. As we can see, the velocity of the fluid has decreased at the outlet. At first it was 1.5 and 0.5, and as the fluid moves to the outlet in midplane, it's decreased a little bit, and at the outlet it decreases. It also decreases to a very gradually. So these are the 2 points I have to explain. Now we will move to analyze frequency effect on velocity distribution. So we have to change the expression first at the inlet. We had given 2 Hertz, so now we will give it 10 Hertz. 10. Apply. So we have changed the frequency to 10 Hertz now. So we will see the effect of change of frequency on velocity distribution. We will give the time step to 0.002 and number of time step, say 500. So this will give us 0.1 second fluid flow from the pipe. Again we will go to report differentiation, new surface report, area weight average, select inlet and velocity. Okay, now this should give the velocity at the frequency of 10 in the inlet. So as you can see, as we change the frequency of the fluid to 10 hertz, the cycle is more compact. There is a horizontal change between the 2 hertz and the 10 hertz. So that's all I have to show in my question to analyze frequency effect on velocity distribution. So this is the frequency effect on velocity distribution, where there is a horizontal shift where in one cycle of 2 hertz 5 more 10 hertz cycles can be fitted inside it. So that's what's all from me. Thank you.